Colligative properties, properties of a solution that only depend on how much solute you use, not the type of solute. So I'll explain an example of this. If I have a beaker, and solute, of course, just means the stuff that's dissolved in a solution. Usually we're dealing with water. So let's say this is a beaker of water, and we've got a bunch of ions floating around in there. And over here next door we have another beaker, and over here maybe these are molecules. So a different substance, but notice I've drawn 5 little dots on in both beakers. So for that reason, because they have the same amount of both solid, because I have the same amount of solute in both beakers, we would expect the same change in freezing point, which is a colligative property, due to the fact that the amounts are the same. It doesn't matter that one of them might be table salt and the other one might be sugar. We're going to have the same lowering of freezing point by adding the solute. So we have to express the amount of solute in the solution using a new kind of concentration that's called molality. And it sounds weird, but it's similar to molarity in a lot of cases. But here's how it's different. Molarity is mole of solute over liter of solution. Molality is mole of solute per kilogram of solvent. Now, usually molality and molarity are very similar in terms of the numbers, but when the concentrations get high enough, it's possible that they can differ a little bit. Because on the bottom here, we're not talking about the volume of the solution anymore in the numerator. We're talking about how much water we had there originally. And so as we dump in more and more salt, it affects the molality and the molarity. But my original mass, my solution's volume is changing as I add more solute, but the kilograms of solvent is not, because that original liter or whatever of water is still the same. So let's take a look at an example problem where you have to calculate molality. So if I have 39.5 grams of sodium chloride dissolved in 500 grams of water, first thing I'm going to have to do is recognize that my 39.5 grams of sodium chloride needs to be changed to moles. Okay, and there it is, just using the periodic table, I changed it to moles. That's my solute, that's what's going to go on top. And then the next step is going to be to change my 500 grams of water into kilograms, because that's my solvent. Okay, so I just divided by 1,000. There's 1,000 grams in a kilogram. And so then the last step is going to be to take my moles of solute, sodium chloride, and divide it by my kilograms of solvent. And I'm going to get 1.35 moles per kilogram. But molality actually gets the symbol, just like molarity is a capital M, molality actually gets the symbol lowercase m. And there we go. So let's take a look at one of our colligative properties, freezing point depression. So freezing point depression, essentially we're saying that the freezing point of a solution is always lower than that of the pure solvent. So like, for example, we know water freezes at 0 degrees Celsius. Well, if I have water with some sugar added to it, that water is going to freeze at a little bit lower temperature. So if I have some solute particles in there, they're going to actually stop freezing. They're going to get in the way of freezing, and that is going to actually bring my freezing point below 0 Celsius. Now, the change in the freezing point can be calculated by delta T, meaning change in temperature of freezing. So delta TF equals Kf times molality times I. Kf is simply the freezing point constant, and this will be provided. You don't ever have to to know what that number is or memorize what that number is. It'll be given to you in the problem or, on the test or whatever. M, of course, is molality. We just talked about how to calculate that. The I in the equation is something called the Van Hoff factor. It's an O, not an A, sorry. Van Hoff factor. And I'm actually going to hold off on talking about that for just a second. It's actually a very simple number, but we're going to talk about that as we get into an example problem. But there's your equation. So let's take a look at a problem. It says, what is the freezing point of 750 grams of water if 85 grams of NaCl is added to it? So essentially, we want to know the change in freezing point because we already know the original freezing point of water is 0 degrees Celsius. So if we can figure out how much it's changing, we can actually just subtract that number from 0. And so we have Kf times m times I. Okay, so let's do this one step at a time here. The Kf is given to us, 1.86 degrees Celsius over molal. So that's taken care of. We got that. Molality is not given to us, but let's see if we can find it. So we have 85 grams of NaCl. Let's go ahead and convert that into moles. Okay, so using the periodic table, I get 1.454, and then my grams of H2O. To find my molality, it's going to be moles per kilogram. Now I'm not going to show my work this time. I'm just going to move the decimal point over 3 times because I know 750 grams is the same thing as 0.75 kilograms. And then I'm just going to divide. And I get a molality of 1.94 molal. All right, so I'm almost done here. Delta TF equals the KF, the freezing point constant for water, is simply a book value that was given to us in the problem, 1.86 degrees Celsius per molal. The molality I just figured out, 1.94. And then the Van Hoff factor is going to just depend on how many particles this compound splits up into, right? So if we look at this, NaCl, if it were to dissolve, would form 2 ions, Na plus and Cl minus. And since each one forms 2 ions, that means the Van Hoff factor is simply 2. That's all you have to do. If it's an ionic compound that contains 3 ions, it would be 3. If it's a molecular compound, well, those don't split up, so it would just be 1. And we'll get to an example or two of those in a minute. Let's go ahead and see what the freezing point change is. Okay, and it turns out to be 7.21 degrees Celsius. And so if you'll notice here, molal cancels here and here. And then we're just left with degrees Celsius for our unit. Now the last step is, the question is what is the freezing point? It's not what is the freezing point change. So all you have to do is take your original freezing point, which is 0, minus the change, because depression means it's going down. So freezing point depression will always be subtracted from the original freezing point, and of course that means we're going to get negative 7.21 degrees Celsius. Not every solvent, of course, has a freezing point of 0, so if it's ethanol or something else, you're going to have to subtract from a different number there. All right. Our other colligative property we're going to talk about is boiling point elevation. So boiling point actually goes up when we add particles. And the reason for that is very simply that those particles get in the way. So if I'm heating up a sample of water to boil it, and those molecules are leaving the liquid state, and I put some salt or some sugar or something dissolved in this beaker, these things literally stop the water molecules from leaving, requiring more energy to get them to leave. And the equation that governs the change in boiling point is exactly like the other one. And the only difference is now we've got Kb instead of Kf, And when we're done, we're going to add it instead of subtracting it from the original boiling point. So let's look at an example. What's the boiling point of 1.5 kilograms of ethanol? And that gives you the KB if 225 grams of table sugar is added to it. And then it tells us that pure ethanol boils at 78 degrees Celsius. So let's figure out the delta TB. Just going to rewrite my equation here. KB times M times I. Now we have to figure out the molality. So first we have to figure out 225 grams of C12H22O11. How many moles is that? Because that's my solute. Okay, and I went to the periodic table and I added up all 12 carbons, 22 hydrogens, 11 oxygens. I got 342.34 for my molar mass, and that gives me a number of moles of 0.6572 moles of table sugar. And then I do have to divide that by my kilograms, so to get my molality. And that means, in this case, I don't have to convert because it's already in kilograms right here in the problem. And so just take my number divided by 1.5, and I get 0.438. And remember, that's molal. So now I have almost everything I need for delta TB. So it's going to be KB, which was given to me in the problem, 1.22 degrees Celsius per molal. And then we just got our molality, 0.438 molal. And our Van Hoff factor for this one, okay, so it's a molecule. And I mentioned this earlier, but molecules don't break up. So the I for a molecule, a molecular substance, is just going to be 1. And in fact, you can kind of skip that step because multiplying by 1 doesn't do anything. But anytime it's not an ion, it's a molecule like sugar, you can just disregard the Van Hoff factor because it will be 1. Okay, so all I have to do is multiply my molality by my KB, and I get 0.535 rounded. Molality cancels, and so that's going to be degrees Celsius. And if I want to know the boiling point, I have to actually, so this is going to be my boiling point, take my original boiling point, 78 degrees Celsius, and actually add that answer. And so plus, so we're going to be at 78.535 degrees Celsius is our expected new boiling point. So very small change, but that's because our molality was pretty low, 0.438, and we had that Van Hoff factor of 1. So that's those are a couple of examples of colligative properties. We'll go through a few more in class, so that bring your questions so we can answer them.